Hi, and welcome to the second part of Lesson 1, wherein I'll be talking everything about complexity analysis and build the foundation for the next parts of the whole series. So let's get started. So complexity analysis is a key important topic when we're talking about algorithms. Imagine there are many ways of approaching a given problem. You can use multiple kind of algorithms and make them solve the problem. But what is the best and optimal solution among the many algorithms that you've created? You identify that by running the complexity, seeing what the complexity of the algorithm is. Firstly, analyzing complexity helps us measure efficiency, both in terms of time and space. The memory usage that your algorithm is going to do, plus the time it is going to take for each operation through your algorithm. Second, it can help predict scalability and feasibility of an application. This is what will help us create a more robust application, and that will help solve the problem we are solving for. The first way of analyzing is the big O notation. It helps us determine the upper bound, or in parallel terms, it can be called to be, it describes the worst case scenario for an algorithm. Consider this, consider linear search. It runs in O of n. Even if the element is found early, big O reflects the maximum possible number of iterations you'll have to go in order to find an element using linear search. Now, the next is the lower bound. It helps you identify the best case complexity for an algorithm. So, for example, for an insertion sort, it will be consider an already sorted data and it takes linear time. The third one, which is pretty popular as well, is the tight bound condition. In this notation, you want to describe the exact bound for an algorithm. For example, it is n log n for merge sort, as it performs consistently in all cases. Comparing all three notations. When we are comparing big O, that is the worst case bound, it ensures that an algorithm will not exceed a certain time or space. In case of the best case bound, you are trying to demonstrate the minimum possible performance. In exact bound, you are determining the average or the most likely growth rate of an algorithm. As the number of entries increase to an algorithm, what would the growth rate look like? Now, now that we have known these, a lot of other places will also teach you about these three things theoretically. But how do you visualize it? How do you actually create sense out of these notations? So consider binary search for a sorted array. Your best case scenario will be O of 1, that is, the target is found in the middle. In binary search, for all of the numbers, you break it down into two and start searching. So if it is found in the middle, that is O of 1, it is represented by the best case. If the target is very much towards the end, that becomes your worst case scenario because you've gone through every search and then in the end only you're getting the final element that you wanted to be found. Exact bound is log n. And another example, instead of searching, let's go to sorting. The best case will be if it is already sorted, it will be O of n. If it is completely reversely sorted, you'll since you're sorting, everything is in the opposite direction. That's the worst case scenario for bubble sort. In that case, the complexity is n square, where n represents the number of elements. And exact bound is not actually applicable because of varying input cases. This should help you get a sense of what does each kind of notation mean and what are different ways in which you can evaluate your algorithm and identify the best fit among the many examples. There are two more additional complexity matrices. The first is the little o notation. It represents a strict upper bound. For example, an algorithm with of n square performs strictly better than quadratic time limit for larger inputs. And the little omega notation represents a strict lower bound. An algorithm which has a little omega n complexity that grows faster than linear time. Let's talk about the practical implications of notations. When you have to identify the worst case risks, especially for critical systems, you go with big O. Then the big omega helps identify if the optimal potential exists for ideal cases or not. And big theta is useful for predicting the average case performance in realistic scenarios. Now, whenever you're working with notations, the trade-off that you have to think about is the space versus the time trade-off. Algorithms with lower time complexity might require higher memory usage. Now, for real-world examples, let's look at four algorithms, that is binary search, quicksort, hash table, and Dijkstra's algorithm. If we talk about the big O notation, you'll see that binary search, it is log n. For quicksort, it is n square. For hash table, it is O of n, wherein you're looking up things, so kind of searching. Dijkstra's algorithm is O of v square or e plus v log v, based on if you're representing it based on the matrix or the list version. In case of big omega, the binary search is the best. So you are able to find it in the middle, the element that is the target element. So it becomes omega of 1. In case of quicksort, it is omega of n log n. In case of hash table, it is omega of 1. In Dijkstra's, it is e plus v log v. So if you see, generally, you'll see that the big omega notation, because it gives you the best case scenario, it is generally less than or equal to the big O notation, because that is the worst. Big theta, on the other hand, is the average that you get. So in the binary search, it will be log n. Quicksort, it is n log n. Hash table, it is theta of 1. In Dijkstra's, it is e plus v log v. This will help you get a sense of what is your actual use case. Imagine your use case is such that you are having random numbers being inputted to you one after the other in your pipeline. In that case, you would want to evaluate algorithms based on the big O complexity. That is the worst. There's a high possibility of cases wherein you'll have exactly the opposite order of numbers that you'll get than what is desired. So if you have algorithm 1, 2, 3, in comparing and choosing which is the better one among these three, you look at what the big O notation, the big O complexity for each of them is. In a case wherein it is going to be like a hash table lookup, and if you know that everything is already sorted, there's good indices already on your table, then probably you would just compare either big omega or the big delta notation. And that will help you decide among the algorithms. So use the different complexity analysis in order to identify the most optimal algorithm for your use case. Now let's look at the key takeaways of complexity analysis. Firstly, complexity analysis helps in measuring and predicting the performance of algorithms in terms of time and space. It ensures that systems scale efficiently with increasing input sizes. Big O focuses on the worst case scenario, which is critical for ensuring reliability. The big omega highlights the best case scenario. It reveals the optimization potential. Big delta provides a tight bound, which offers a realistic performance estimate. Thank you.